Let's have a look at nuclear imaging and radiotherapy. This is Dr. B, and we'll be approaching this from a introductory college level. This is the material that's required for an international baccalaureate course. Well, nuclear imaging and radiotherapy are important techniques. These first three are imaging techniques. We can have SPECT scanning, which is single photon emission computed tomography, which is different but in some ways reminiscent of, say, the barium swallow technique, where you take barium and you see it light up all over your body. You'll see an image here that using this to detect a foot issue. See how it lights up right there? Take a look at PET scanning, and this shows some this method, positron emission tomography, applied to looking at Alzheimer's patients and detecting them. Magnetic resonance imaging, MRI, which most of you are familiar with. This does not involve a radionuclide, whereas all the other methods do, but it's similar in that it's nuclear-based, so we'll have a look at that. Radiotherapy, which is still a common technique for cancer therapy. And an experimental technique we'll have a look at is called targeted alpha therapy, which shows some great promise. So let's take a look at the first three imaging techniques first. A SPECT scan needs some sort of radionuclide, and in this case we'll be looking at technetium-99 complexes. These are beta emitters. They're gamma ray emitters. So they'll give off some energy, and that can be detected, and you can see where it is on your body. You might want to look at it for, say, a blockage, for example. A neat thing about it is you can tune these complexes to go to different parts of the body, either the brain, this is the form of this substance, or the heart. They give off gamma rays so they can be detected. The nuclear reaction is shown here. I showed two because first you have to generate this stuff. It only has a half-life of 6 hours, so you need to store it in the hospital and then be able to use it when you need it. So initially, you take some molybdenum-42, which can then be used to undergo a nuclear decay to give rise to technetium-43. I'm going to say that is positron emission, but I could be wrong. It could be just a beta emission. And then that once you have your technetium-43, it then undergoes, and that should be a 43 right there. It then undergoes gamma emission, and that's where the detection takes place. This is great for soft tissue studies, whereas X-ray would not work for these. The technetium-99 is a good choice because it has a short half-life. It gives enough energy to be detected, but not too much. It can easily form regioselective complexes, and you can make it when you need it from in the hospital from molybdenum-99. PET scanning is an imaging technique which uses fluorine-18 compounds, I believe, are the most common. This is fluorodeoxyglucose, so this is a glucose molecule with fluorine substituted here, but not just fluorine. This is fluorine-18, that particular isotope, which is a positron emitter. That means it's going to give off that substance there, which means this is a beta emitter. That's a beta emission, beta particle. Fine. So once it does that, it's going to be detectable just like all these other techniques, and this is particularly good for tumor visualization since F-18 can accumulate in cancer cells. So PET scanning is a great imaging technique. MRI is perhaps the most common. It is not a radionuclide-based process, which means it's a lot safer. It's a nuclear magnetic process, which I won't go into the details of. There is no nuclear reaction. This is used in cases where you're dealing with soft tissue. If you're dealing with bones, X-rays might be better. But it's the same principle as chemists familiar with nuclear magnetic resonance. It will map all your hydrogen atoms, and it's a non-hazardous technique. For radiotherapy, this is an external process. There's the external device that's focused on a cancerous region. Cobalt-60 is oftentimes used. This is a high-energy beta emitter. So you're not using this for imaging. You're using this to destroy the cancerous region. There's the beta emission process. Notice that it is a beta emitter. right? Just like that one is there. And it does involve some high energy gamma rays also, which you want. This can be used for solid tumor treatment. Point it at the affected area and off you go. But what if you have a non-solid tumor? These are harder to deal with because they're systemic. They're all over the body. Targeted alpha therapy might be a promising technique. You take a radionuclide, lead-212 in this case, and you bind it not to a simple substance but to an antibody that is in principle selective for a cancerous region. Imagine the utility of that. Sometimes referred to as a warhead technology. This is an alpha emitter. These are give shorter distances of their activity, right? This thing you can zap it down from far away, but an alpha emitter has a much shorter distance that it covers of because it's an internal technique. You want that. And this would be alpha emission of lead-212. When you do that, each of the molecules will then, in principle, and I hope it's true, go to the tumors wherever they are in your body, and they can be all over. It doesn't have to be regiospecific. They then undergo alpha emission, which is a high energy, short range emission, which targets those regions and has great potential for non-solid tumors. Perhaps it's a little bit like targeted bomblets. They each go to different regions. This is a look at nuclear imaging and radiotherapy.